G'day everyone and welcome to today's presentation. So yeah, Alistair covered off the topic for today and basically who I am as well. Just hang on a sec. And so just a little bit about Pryda, established in 1964 in New Zealand. The head office is in Melbourne, and we also have subsidiaries around Australia and New Zealand. We're part of a company called ITW, and they're some familiar, well-known building product names there that you probably recognise. Our core business is really engineering, design software, frame and truss manufacturing equipment, and the manufacture of timber connectors. So steel timber connectors for the frame and truss and the residential division. So if we look at the legislative framework for light gauge timber, it's governed by the NCC 2019. Most of the design is primarily done through the 1720, the AS 1720, and the installation and design also is covered by a document called the AS 1684. So, and AS 4440 covers the installation of roof trusses. So they're the sort of governing documents that you need to be familiar and aware of when designing residential buildings. So if we look at how this sector is serviced, we've basically got building plans come in, it goes to architects and engineers. They create the drawings and the specifications, which then go to the off-site fabricators to make the frames and trusses. Those go to site, and then the certifiers obviously check the installation, the compliance, and sign off. So our business is located in this engineered truss systems. There's two other players in that market space as well, and there's also serviced by a number of solid timber engineering design companies that supply LVL and I-joists into this fabrication and on-site channel. So if we look a little bit more at this sector in detail, essentially what happens is the building plans come in, they use our software to create these 3D models with the frames and trusses laid out. Those components get sent off to the factory where they're cut by automated saws, and then they're assembled on manufacturing equipment and then sent to site. So the scope of today's presentation is essentially going to be timber roof trusses, timber wall frames, and timber floor trusses. So if we have a look at some of the fundamental principles first, before we go off and create efficient designs, we need to be aware of some of the terminology involved and some of the fundamental principles and benefits of trusses. So if we look at the way that a truss is created, it has top chords along the top here, which support the roof loads. It has a bottom chord, which supports the ceiling loads, and then they're interconnected by these members called webs. And those web joints and the connection between the top chords and the bottom chords are plated together with these steel plates. Okay, and they're located at these positions called panel points along the truss. So if we look at how a truss works, trusses work on a thing called triangulation. So if we look at this particular setup here, we've got two opposing rafters with a load on it. What happens is this load comes down the outside of these chords and pushes these supports out laterally. Okay, so if you've got a wall here and a wall there, without some other form of connection in there, it's going to push these walls out to the side. So if we look at how triangulation works, when you introduce a bottom chord into the timber frame here, the load comes down this outside and then gets redirected down through this bottom chord, and so then it becomes a stable mechanism. So if we look a little bit further on how these loads are transferred in a typical type of truss, you'll see that the loads are usually a lot higher on the top chord. They cause compression in these members here, which then cause these loads to go up the webs and then back down the top chords. So that's the way that trusses work. They effectively redistribute these loads around the truss to make sure that it's stable. Now, if we look at how trusses deflect, they usually deflect in two primary ways. One is basically the outside profile of the truss, which is shown by these blue lines. So as a complete section, this truss will often deflect downwards. And this is often mitigated at the manufacturing stage by introducing what's called camber into the truss. So what they do is the software knows how much it's going to deflect downwards. So what the fabricators do is actually create a hog in the bottom chord of the truss when they're making it to mitigate the effect the truss is going to deflect. The secondary type of deflection is actually in between these panel points. Okay, so when you load it up, these members in between these panel points will deflect as shown. and we call that interpanel deflection. So if you put those two together, you get the outside profile of the truss deflecting, and then these members in between the nodes deflecting as well, which creates the final shape. So some of the benefits of trusses, they're incredibly stiff when they're loaded in the vertical plane. So just to give you a good example of how this works, we're going to look at a truss, 5-metre span with a 25-degree pitch with a 10 kilonewton point load, which is about a tonne, and we're going to compare it to a steel beam, which has got the same loading conditions on it. So at 5 metres, we've got 6 mil deflection at the centre of the truss and 3 mil deflection on the steel beam. So if we now double the span, same loading conditions, we can see 12 mil deflection in the middle of the truss, 28 now on the steel beam. And the fact is that these steel beams can often cost thousands of dollars, whereas a truss like this is often in the hundreds of dollars. So a lot of cost savings and efficiencies there. So if we drill down into this in a bit more detail, why is this timber truss outperforming a steel beam? And it's related to some of the fundamental properties of how trusses operate. So if we look at this formula here, don't get too scared by this. This is basically the deflection for this particular beam is determined by the point load that's on there, the span of the beam. One thing to note is this span is actually cubed, so that causes this number to increase exponentially, and then it's divided by 48 EI, which is E is the modulus of elasticity and I is the moment of inertia. So these are two types of fundamental properties of the timber and the sectional size, which look to counteract deflection. So what you want is this number on the denominator to be a lot larger than this number up here. So if we look at how that plays out, the I value for a typical beam is calculated by B H cubed on 12. So you've got the base dimension, this number here is cubed, and then it's divided by 12. So if you look at the same size beam oriented vertically to oriented on its flat, this I number is actually 32 times larger on this particular beam here than on this one. So fundamentally, we want to try and maximise the depth of any timber design member that we get, because we get these exponential benefits in the moment of inertia value. So if we compare this between timber and steel, we can see the E value for steel is 200,000 megapascals, whereas with timber it's anywhere between 10,000 and 14,000. So we have to remember this value is 20 times smaller than this. So the way we have to try and counteract that is by maximising the depth of the beam. And you can see these are two equivalent. So a 200 by 35 steel beam is equivalent to a 542 by 35 timber beam, because this I value counteracts the difference in the E value between these two. So if we go back to the timber truss example, the reason it's performing so well is essentially at this centre part, it's almost 2 metres deep. So our effective I value is really massive, which is counteracting the E value from the steel beam. So just move on to how to design these things more effectively. What you want to have really the most benefit on site is having your key stakeholders all talking together and communicating together. Sometimes a lot of these site issues are caused by a breakdown in this communication loop here. So, and the best thing to do is to leverage each stakeholder's expertise. So these guys in this fabricated channel are often really good at being able to locate and run trusses around conflicts in typical residential design. So try and leverage that whenever possible. So accurate plans, real key thing. May sound simple, but accurate plans really count towards maximising efficiencies on site. So get all the information on the plans before you start. Key things: mechanical services, solar panels, solar hot water systems, any safety anchors and skylights, and the durability requirements. Trusses are great inside in protected environments, not so good outside. So you need to keep them dry, isolated from weather for them to perform effectively. So if we touch on mechanical services, which is one of my favourite areas, it's funny that air conditioning units form nearly every modern construction these days. However, they're frequently left out of the design plans. So in this digital age, I feel we should be doing a lot better with this. So the beauty of trusses is they're 95% air. That's why they're so cheap and efficient, because they're all these are void spaces in the middle of the truss. So you can usually fit things quite easily into the profile of the truss. So these air conditioning units will often fit nicely into the void spaces. However, the key thing to note is that as the pitch of the truss decreases, so does the allowable void space. So you need to allow for this when you're designing, otherwise they might not fit in. A typical site example, which has happened recently, was a set of series of shallow pitch trusses, and the air conditioning unit was left off. So we had to try and figure out a way to locate these air conditioning units within the void space of the roof. So we had to cut all these trusses off, run beams parallel, and drop this ceiling, the air conditioning unit into the ceiling space. Now, the other thing to remember is that it's not only the air conditioning unit, it's the ducting that goes with it, okay? So the ducting needs to run somewhere. The shallower your truss becomes, you get conflicts with the webs, and so sometimes you have to cut them out, so you have to run these ducts through there. So if you allow for that in the planning and development stage, saves you all the headaches on site. And the key thing is that, you know, schedule of works won't stop as well. So if you have an issue like this, you've got to pay for engineering fees, you've got to pay for rectification fees, cost of all that, and it stops your schedule of works on the job as well. So even more important when you have non-flexible ducting, so these are preformed steel ducts, because these can't be just reshaped and run around the conflicts. So you need to make sure that if you're using those, that you accurately map where they're going to be going and what height, so these webs can be moved out of the way when the fabricators are doing the design. Okay, so if we look at these sorts of things, if you plan ahead, you know, these void spaces can actually be created in the roof space to allow your air conditioning units to sit in there. And then just remember where these ducting ones are going to go. If they're mapped as well, then they can create conflict areas within the software to allow these webs to be run around those conflict areas. Another one common sort of theme as well is skylights. So if you have a look at skylights, we've almost done the job really well here. This is the plan from site. You can see the skylights are highlighted in red, and you can see on the design model, these have been pulled through to the design model. But unfortunately on the architectural plans, what they missed was that the actual skylight had a raking shaft at the back of it. So instead of going down vertically down into this void space here, the back of the shaft actually raked down this way. Okay, so really key to get those sort of details mapped on the plans, so the guys that are designing these frame and truss components can design around it. So in this case, all these trusses had to be cut and rerun and fixed on site, which just creates inefficiencies and costs and delays. So if we look at box gutters, another common on-site problem. The shallow pitch of these box gutters, they're becoming more prevalent, and they require careful design considerations, okay, because the shallow nature of these trusses tends to work against the natural benefit of trusses, which is utilising the depth. So try and get these minimum depth requirements at the stub ends as high as possible, so you can get these stiffness benefits that trusses have with the depth. The other common issue that these types of components have is with the dwarf walls. So lots of builders just put basically a dwarf wall frame on top of the bottom quarter here, but when you get a wind load coming in from the side, this will tend to pivot around this base here, okay? So what you should have is a moment resisting connection at the base between this upstand and the bottom chord of the truss. Okay, that creates a stable mechanism, so any wind loads are basically taken around this heel joint of the truss. Okay, so if we look at this in sort of action, these are the sorts of design details that fabricators have. They can plate up these L frames separately to the truss, and then they can be stitched on site. So they can basically be site enabled, screwed off to the side of the existing truss to form these stable parapets. You can see the little claw plates here, which are creating the moment resisting connection at the base here. Okay, so leveraging innovation as well. So innovation's a key thing for our company, and looking at new ways and inventive ways to utilise the benefits of different types of mechanical fixings. So if you look at the old way was essentially multi-grips. So fixing this thing in with nails into the side of the top plate, into here and into the truss. So time constraints, and nails aren't really that effective in terms of their shear capacities and their withdrawal loads. So these days, systems are available to have the screws pre-installed into the truss heels, and driven down into the top plate. So it also saves your labour efficiencies that with this particular thing, you have to go and skew nail the truss heels down into the wall plates, then go back and fix these multi-grips after the trusses have been installed. With this system here, you come and drop the trusses in place and drill the screw down into place, and it forms the initial connection and the tie-down fixing as well. So leveraging those types of systems saves you time and money on site. You know, there's efficiencies up to half a day that these particular systems are creating for installers on site. The other benefit that's a real massive one is the mechanical benefits of these particular systems. So if you look at a screw, the profile of a screw versus the profile of a nail, when you drive a screw into timber and try and pull it out, it's got all of these threads running up the shaft of the screw that are all engaging with the timber. Whereas you look at a nail and it's all smooth, and the only resistance that it's providing when it's being drawn out of the timber is this frictional resistance on the side of the shank. So if we look at the actual screw performance here in this chart, you can see that the nail is way down here. Okay, you've got a typical Type 17 screw, and then the speed truss screws are really carving out the maximum performance when you're driving these things into the top plate. So utilise those efficiencies. So just in summary in this section, trusses have a super high degree of stiffness and are one of the most effective, cost-effective options for spanning from 5 to 20 metres. Make sure your plans are accurate and contain all the relevant design information to avoid costly rectification and on-site delays. Be especially careful with shallow pitch roofs that void spaces are allowed for the AC units, and the ducting runs, really super important. And make sure that the parapet box gutter ends are formed with moment-resisting joints, not dwarf wall frames just stuck on top. And utilise the innovative connectors to create efficient designs and create on-site installation savings. So now we'll just move on to timber wall frames. So that's a typical type of wall frame. These wall frames are mostly from fairly simple beam and top column type connections, so you have to think a little bit more laterally on how to create design efficiencies for these members. So if we take top plates as an example, top plates are made of slender members and they're prone to deflection between the studs. So when you're designing and specifying these elements, the way to maximise the benefits is design the studs directly underneath the roof trusses and the floor trusses. And that way you take that bending and shear out of the top plates and direct the load straight from the truss into the stud. Okay. And uplift as well. So it's a common theme at the moment. So when you're designing and fixing top plates on site, you have to take due care and consideration of how it is tied down, because that really affects the performance of the way these top plates work. So if we have a look at a typical example, under uplift, the fixing ratios are determined by the span of these tie downs, not the stud locations, but the tie down locations. So when the uplift is applied to these top plates, you get a reverse bending in between these tie down locations. Okay, so we can see the stud tie down location or spacing is set to 600 here, and the capacity ratio for the top plates is around about 45%. If we then go and move one of the tie downs, so take the tie down off this wall, then the top plate has to span between the next set of tie down locations. So you can see with the same loads on it, setting the tie down spacing to 1200 rather than 600, the capacity ratio jumps from 45% to 90%. So to optimise those sorts of things, you need to have your tie downs in the right locations and making sure they're working for you properly. So if we look at gravity loads tend to engage both of the top plates. Okay, so when the loads are acting downwards, even with site nail fixing, because the loads are acting downwards, they're pulling both of the top plates together over these studs. Whereas if you look at a top plate design that's being pulled upwards, which is under wind uplift, you tend to get this separation over the studs here, because both of these plates are being pulled up together, but the way to mechanically fix them is with nails, which are, as we talked about before, are quite ineffective at holding these members together in withdrawal. So they tend to separate, so they don't act effectively together. So the best thing to do is to try and provide fixings that engage these plates effectively. Okay. So some simple things as well, designing lintels. So this may seem obvious, but try and create roof patterns that take the load off the longer span beams, and then you can create more effective and economical beams. So you can see in this particular example, normally they would run the TG this way onto this garage beam. So we're looking at this garage beam spanning a long distance through here. So rather than having the full span trusses running this way, what they've decided to do is run the trusses parallel with the beam. So that takes most of the load off, and then you can see the only load landing on this beam here is these small span jacks and creepers. So we've reduced the load on the beam. The beam becomes more efficient to design. You may even be able to switch from a steel beam to a timber beam and save yourself possibly hundreds of dollars. Another common theme at the moment is, as designers and open plan living is being pushed, these design envelopes are being pushed as well. So the bracing needs to be considered at the specification stage to optimise outcomes. So as you can see here, typical sort of plan these days, you've got a great big sliding door through here onto a deck. Your actual bracing walls are these tiny little nibs in the corners here, okay? So they're really hard to stabilise. In terms of wall bracing, the A1684 covers wall bracing. They're effective down to about 900 millimetres because then they start getting reduced in capacity. Below that level at 900 down to about 350, there's proprietary systems that are available from suppliers that are basically a cantilevered column, which is a vertical floor truss. If you imagine, it's tied down at the base here and creates a cantilevered column to restrain the building. Okay, and they're effective down to 350 because once you start getting below 350, mechanically those loads that are generated at the tie-down support start to become too high for it to become stable. So below 350, normally you'll see a type of steel portal frame. Okay, so these are highly cost inefficient, but sometimes you're left with no other choice than putting these in because of the width of bracing that you're allowed. Okay. So trying to create on-site efficiencies is really industries moving towards panelisation. So having these wall frames made off-site rather than on-site, and then they're craned into place, just creates labour-saving installation benefits as well. And they usually have automated technology which can do nail bridging and all these sorts of things. They have accurate nailing patterns and everything's designed off-site. So in summary for this section, optimising design and fixing to ensure compliant and economical designs. Run shorter span trusses on the longer span beams to create economical designs, and be flexible with your plans and your layouts of your designs to accommodate bracing. So one option to look at in the planning stage is possibly reducing the window sizes to fit cheaper timber bracing options. So if you're looking at a couple of $1,000s for a portal frame versus a couple of $100s for a timber cantilevered column, it's much better to try and reduce the window size and optimise the design so you don't have that costly outlay for a portal frame. And utilise panelisation construction to leverage on-site installation benefits as well. So if we just move quickly onto timber floor trusses, we've got two main options. One is the metal web profile. Some of the features and benefits. They're usually a fixed depth, so these webs come in fixed depths, so 250, 300, 450 as well. They're lightweight and economical, so they're not as heavy as some of the timber webbed versions. There's set downs available, so you can do set downs for wet areas, and they can span up to about 6.9 metres. The timber web is the more premium performance type product, higher degrees of stiffness, and really flexible with their depth profile, so they can basically create any depth with these timber members. Set downs are available, a bit like the metal web profile, and spans up to 7.4 metres, so some really good open spans there if you can get them deep enough. So some of the key benefits, you can see these set down areas that can be created and designed in the shower areas. One of the main benefits is having these open web systems, so you can run services through them without having to cut eye joists and things on site. You can run these through. There's no cutting, drilling or notching on site. One of the other key benefits is the end types. So really flexible with their end type profiles, so you can mesh them into steel beams, create ledger plate fixings for brickwork, top chord supporters on the steel beams. They're really a variety of end types to create all of these types of connections. Another major advantage is the specification and support documents that are available. So on the websites of these suppliers, they'll have all of these fixing details, so you can put all these connections in and make sure that they're compliant when the certifier comes calling. And one of the other advantages, again, panelisation. So as this starts to become a bit of an industry topic, these panelised systems can be created off-site, fixed, and then craned into place. And so you can save a lot of installation time by having these panelised systems turn up, dropping them in with cranes and fixing them together on site. So if we just run through some of the benefits of floor trusses, utilising their open web profiles to run services. They have an extensive design and end type flexibility, so utilise it to save cutting and packing joists on site. Providing accurate and detailed plans, which is our common theme for the day, so that the conflicts can be noticed by details and accommodated during the design stage. Use documents and specifications provided by the suppliers that are freely available on the websites to accurately install components, and leverage these off-site assembly options like cassettes to create on-site installation efficiencies. And that's the end of today's presentation. Thanks for your time.
So we did have a couple of people just on chat. If this is going to go backwards, just asking about what the questions were. Is that not moving for me? Okay, so just if you didn't take them down before, these were the three formal CPD questions. Perhaps just take a screenshot of that for those people that missed it before. Okay, let's jump forward to the Q&A. We've had a number of questions here, Ian, so a great presentation, some really good sort of practical points that you raised there. Actually, this one here, which a number of people have endorsed, which I have heard before, why is the TRUSS design software only available to fabricators and not to engineers and designers, I'd imagine, to allow for some sizing during the design process?
Yeah, that's a good question. Look, that's been the methodology we've used over these years, is to have that software available and partnered with the fabricators. Basically, because a lot of the functionality of the software is that assembly as well. So it's usually linked in with assembly methods, so cutting and fixing. So that's the path we've just historically chosen for putting the software out into the marketplace. You know, it is an engineering piece of software. We looked at options to, you know, potentially host it in that sort of environment, but at this stage we haven't. So that's been the pathway we've chosen.
Mm-hmm. And there was interested also in the pre-installed screw fixing. So a question here, the pre-installed screw fixings from the truss to the top plate, when inspecting, how can one tell if they are installed without climbing and checking?
Yeah, sorry, I just broke up at the end there, Arthur, but I think I know the thrust to that question. Yeah, so when they're installed on site, normally the best thing to do is, you know, to get there before the roof shooting goes on, and then you can get around the perimeter of the building, because you can usually see most of these connections from outside the perimeter of the building. If you don't have that opportunity, because there's buildings on either side, then yeah, usually just a small step ladder is just to get up and have a look down the run of trusses. You can usually see, you know, most of the connections along those external walls just by getting up on a small step ladder and looking down the run of those trusses, and you'll easily see which ones are in and which ones aren't. The other way to do it is to use a selfie stick mirror. So you just put your camera on the end of a selfie stick, telescopic lens, and just move it over the heel of the truss, and then you can easily identify the screw in place. Yep.
And you also mentioned with some of the aspects about design of the truss, about photovoltaics. Yeah, what are the requirements that can be specified for roof trusses?
Yeah, normally there's two sorts of considerations for solar panels. One is when they're flat to the roof. So normally that's just the weight. So when you get a wind load over the top of the roof, it tends to have a suction pressure on the roof. So when the solar panels are flat to the roof, then that's reasonably okay. You just need to consider the self-weight of the panels, which is usually quite light, usually 10 to 15 kilos a square metre. So it's not not a major consideration. Where it does start to get a little bit hairy is when they start putting them on raised platforms, because then you get two sets of wind loads on the roof. You get the wind load on the solar panel, and then you get the wind load on the roof itself. So those types of considerations need to be flagged early in the design stage, so that those reactions from those raised platforms can be added to the roof design in the process. So those are the sort of two key distinctions for solar panels. But mostly flat solar panels, minimal impact to a roof. They're quite light. They're 10 or 15 kilos a square metre, and the roof truss will usually cover those pretty easily.
Mm-hmm. And a question about what is the recommended minimum pitch for a roof truss system?
Yeah, look, we're going through that at the moment. We're seeing a lot of 1 and 2 degree pitch roofs, and that is okay normally. Sort of 2 degrees is around about that point where you'd say, okay, that's getting a bit hairy, but it's really that end depth. So if you can get enough end depth at the truss, then those 1 and 2 degree pitches can still be quite stiff along their span length. It's when that heel depth or the depth of the external wall starts to drop away, you lose all of the benefits of the truss, because it doesn't have the depth that generates its stiffness. So those are really the key things, is to try and optimise those profiles. If you're using a 1.5 or 2 degree pitch roof, make sure at the box gutter end or the external ends that you're trying to maximise the depth at those ends. So we usually around about 300 for box gutters is around about the mark that we try and recommend as the minimum, and start working up from there in terms of that end height.
Okay, that's good. You answered another question there that was asked as well. Another one, actually, I haven't heard this one before, says we've had trouble with acoustic outcomes using metal floor trusses with creaking floors. Do you think the timber trusses perform better, and has there been any improvement for this with the metal web option?
Yeah, we don't really get that much in residential. That's probably more multi-residential when you have separate apartment dwellings. But yeah, look, we haven't had too many issues with that, because most of the acoustic and those sorts of issues are created by the interconnection between the wall leaves. So if you can create enough depth, that gives you sort of a cavity area where sound you can insulate quite well. You also need separation between the leaves of the wall frame, so that sound doesn't transmit through the wall frame. So those are the two real key areas to target.
Yep. Actually, a question again about the screw option for holding down the trusses. What is the value of truss hold down of the mentioned screws compared to triple grips? Yeah, look,
the great thing about screws is the embedment depth that they can work with. So on a 70mm top plate, you're generating close to 6 kilonewtons for a pull-out load, whereas a multi-grip's around about 3. So those are the real significant benefits that you can have with these types of screwing systems, and they're much faster to install and a lot more efficient in the way that they utilise their tie-down loads. So if you're looking at a 35mm plate, they're probably around about the 3 kilonewtons for a screw, because you don't have that same embedment depth. But once you go to a 70mm top plate, then yeah, you're pulling up around about 5.5 to 6 kilonewtons.
Someone did ask about, will the presentation be available online later? Yep, as we mentioned at the start, it certainly will. It'll be uploaded over this week, so you'll know when that's up there. Here's an interesting question here, Ian, just use of trusses in snow zones. So when trusses are located in zones as per AS11, what code would you follow for erection, as AS1440 excludes applications where trusses are subject to snow load?
Yeah, generally, within reason, I use the 4440 for that anyway. So with snow load, you generally get more compression in the top chords of trusses in those snow loaded areas. And it depends whether it's alpine or subalpine, but in subalpine areas, I generally, as long as the truss spans aren't getting out to ridiculous levels, I generally use the 4440 as my primary guide for bracing, fixing there. Alpine loads, yeah, they probably just need a bit of a fundamental check on the compression in the chords of the trusses to make sure they're not getting too ridiculously high. But in most cases, I would default to the 4440 and use that as the fixing detail anyway, even in snow loaded areas.
Yep. Another question around bracing. Do truss designers ever specify bracing required in walls to suit their specific truss designs, or are they just assumed to be covered by the project designer or engineer?
That's a good question. Yeah, look, a lot of it depends on which jurisdiction you work in. So in a lot of areas in New South Wales, typically, you'll find that a lot of that bracing gets pushed back to the fabricators, and they'll be asked to provide the bracing details for the wall frames for the house. And typically, you should be able to do that with the 1684. It's a reasonably comprehensive document in terms of bracing. But you move on to different areas in Victoria and Queensland, and some of the engineers are doing that, designing bracing systems in there. So yeah, it's a bit different based on the different regions. But typically, you know, with residential construction, you could follow the protocols in 1684 and get a reasonable result. It's really those, as we highlighted in the presentation, some of those end walls are starting to get really narrow bracing units, and that's at the end of building runs where there's garages and those sorts of things. They're the areas to really focus on, because those narrow walls are becoming more and more prevalent, and you can't obviously put bracing in a wall that doesn't have any width available. So they're the areas to really consider when you're designing and specifying these buildings.
Yep. A question here about the maximum parapet height that can be provided as part of a roof truss.
Yeah, look, 90 mil, probably around about 900 millimetres is starting to reach the threshold, and then you need to start to go to a wider timber. So you can go higher, you can go to 1200 and 1500, but you need to make sure that that parapet width, so that upstand part becomes wider, because then you get a higher moment resistance once you put the plate on. So that wider vertical parapet and the bottom chord, you can generate a higher fixing capacity. So yeah, look up to around about 1500. You're looking at 120 and 140 mil timber. And that's about the cut-off point, around about 1500 for parapets at this stage.
And is there any sort of guidance on how much weight you can put on the bottom chord of a truss for something like an air conditioning unit?
Yeah, look, air conditioning units are usually the loads are pretty easily taken. They're usually around about 100 kilos, and they're supported over 2 trusses. So you're looking at sort of 25 kilos for each support point over potentially 2 trusses. Trusses will take that load pretty easily. When you start getting into the commercial space, then that's when it can all get a bit more interesting, because they can be a couple of 100 kilos, and then you need to just point load the trusses and be efficient in the design. So when you point load a truss, if you load it at those panel points, as we indicated on the presentation, if you load them there, you get a really good result, because the loads go straight up the webs. If you load them in between the panels, then the panel will go into bending and deflection, and because they're only thin, sometimes they can bump up a grade or 2. But yeah, really just taking those loads and putting them in the most efficient point on the trusses is the key way to go. But for most residential jobs, easily take 100 kilos in the roof space.
This is an interesting question. Again, I haven't heard this one before, but did the roof trusses ever deflect too much, bowing the ceiling down, maybe due to timber warping over the years or some defect in the timber? And what would be the best way to rectify these without removing the trusses and replacing them? Can you rectify it somehow in place?
Yeah, that's a good question. Yeah, we get a few of those issues with settlement over the years. A lot of it's traced back to slab movement. So slabs can move at the heels, the trusses move with them, and they can cause cracking at the centre cornice line. So you want to make sure it's the truss that's the problem and not the slab, because that can often be a site condition. Everyone looks at the crack on the wall and assumes it's a truss, but as we pointed out before, the trusses are really stiff, capable of carrying huge amounts of load. So it takes a lot to pull them out of position. But yeah, look, if you do have those sorts of things on site, the best thing to do is target them early. So get them in early into the installation process. And usually we just, rather than jacking and propping and trying to rectify trusses on site, we can just fix cleats to the bottom chords of the trusses to even out the ceiling plane through the run that it's a little bit uneven. That's usually the most beneficial way to do it. If you're doing that post trusses installed, then you probably have to take the ceiling line off and run those cleats in, but that's still probably a better result than having to jack and cut and prop trusses off internal walls.
This is an interesting question we get these days with homes in particular that, people want huge big windows in them and not much room for bracing. Could you elaborate on wall bracing elements between 350 millimetres and 900 millimetres? Like what type of wall elements would there be for that?
Yeah, look, really they're, that sort of space is usually of a thin plywood frames with rods. So the problem is once you drop below 900, the capacities start to get ratcheted down by the standards. So you get reduction factors up to 50% of the bracing value that's above 900. So you get a really large reduction in the bracing capacity. So once you start moving below that, then yeah, they need rods. They either need rodded systems down into the slab, or those, the systems that we looked at, which we call the wall truss braces. They can be effective from 900 down to 350. So, if you utilise those types of systems, you can create some efficient bracing designs without having the onerous requirements of plywood, which might have to have rods, tie-down rods from the top plate into the slab, down to a 350 mil wide. And the only reason that's limited to 350 is really the manufacturing of it. So you still need to create a space where you can run these webs in. And the other thing is the tie-down requirements start to become a little bit onerous, because they become so narrow, the mechanical benefits start to work against them below that 350 mark.
There's still got some good questions coming in here. Have the screw systems been tested and accredited, or are they a performance solution?
No, they've been tested, yeah. So we've tested them in NADA laboratories. We've done a lot of testing over the last 12 and 18 months. We've tested them at various angles in a different beam and wall plate connections. And the design values are all certified by the NADA labs that we've taken them to. So yeah, they're actually a certified connection.
And a question here just on the cassette floors. What is the recommended method for stiffening a portable floor or cassette floor during the lifting operation?
Yeah, we usually run strong backs, which are like a vertical beam through the webs and fix them onto the vertical members of the floor truss, and then use it to lift from there. So it's essentially those beams, once they've got the lifting anchors fixed onto them, then they become the lifting mechanism for the floor trusses. So we don't actually lift from the floor trusses, it's from those beams that run through the flooring, and we just design those beams to take the loads of the trusses during the lifting phase.
Yep.
So yeah, just constant gridding of those beams, usually 4 panels or 4 lifting panel points, so 2 beams at each end is enough. But if you start to get longer runs of floor trusses, then you have to go to a spreader beam and 6 or 8 point connections, and then you might have 3 or 4 of these perpendicular beams to the floor truss span running through the cassette, so you can lift it up in one go.
Mm-hmm. And is there a maximum eave cantilever for a truss?
Yeah, look, you can go fairly long with a cantilever. We've done 1800, 2.4, but you really need that depth over the wall plate. So 90 mil framing is not going to cut the mustard beyond 1200 normally. It just deflects too much, and you get performance issues out on eave corners as everything starts to cantilever and the loads get higher. So yeah, look, sheet roofs, you can go a bit further with sheet roofs because the weight's a bit lower. But depending on how you run your eaves and the cantilevers, you can end up sort of 2400 off the wall frame if you can get enough depth over that heel.
This is an interesting design question. In your experience, have you used any part of the ceiling as part of the diaphragm action to reduce the size of the bottom chord?
No, look, the ceiling diaphragm is the bracing stabilisation for the truss. So the truss actually relies on that mechanical fixing between the ceiling plasterboard and the bottom chord to stabilise it. So it forms a buckling restraint for the truss. Once that ceiling drops away from the truss bottom chord, you have to introduce another system to stabilise it, which is usually bottom chord runners and speed brace as well. So need to be a bit careful with that. The plasterboard actually is the mechanism. So rather than trusses passing their load onto the plasterboard is the is the stabilisation mechanism for bracing buildings, essentially. So the loads, the wind loads that come on the walls and the trusses, it's the plasterboard that transfer those loads to the bracing walls. So yeah, so pretty critical. Even though it's plasterboard, it forms a pretty critical function in terms of building stability.
I noticed there was a couple of questions here about roof pitch. So they're sort of differing ones, but one about minimum roof pitch and maximum roof pitch. You might just want to just cover off on that. There's a question, isn't the minimum pitch under the BCA cannot be less than 15 degrees? There was one later about asking about the maximum roof pitch.
Yeah, I'm not aware of that, but the maximum roof pitch, the software will design pretty much anything, but if you stick within the residential code, it's 35 degrees. So if you're within that residential design code, which is the 4440 and the AS 1684, it maxes out at 35 degrees, and then you have to seek engineering assistance. But the software will take pretty much any roof pitch you can throw at it these days. Minimum, same thing. It drops down to 1.5, 2 degrees, but then you need to start working on the end height so you can create enough depth in the truss to make it work. Otherwise, you may have to switch to rafters or some other sort of mechanism, because the trusses need that depth to run their webs in. So you can go down quite low in terms of roof pitch and still have it work if you've got enough depth to work with at the support ends.
This was quite an interesting suggestion. I imagine the answer is probably about sort of lining the truss over the stud, but it says, wouldn't it not be easier to inspect screws if they were fixed from below? Has this been looked at as an option?
Yeah, look, it is. It's there's all types of systems out there that have different types of fixings. We've gone with the above the wall approach, and we don't think it's too onerous to get on a small step ladder and have a look down the outside of the walls, and it gives you benefits in terms of the way that it's mechanically driven in as well. So there's a lot of installation benefits because you don't have to nail the truss off and then come back later and put the screws in. So yeah, look, it's horses for courses, but I think there's no real detriment to just getting up on the small step ladder and looking down the run of trusses.
Another interesting question here as we talk about more prefabrication, particularly in the residential sector, as opposed perhaps to the mid-rise one. But what are the modern advantages of prefab systems? It says truss here, but it could be floor systems as well. Over on site in situ frames, is not prefab just moving the labour cost off site?
Yeah, a lot of that is some of the benefits. The design benefits are not not groundbreaking design benefits, but sometimes the efficiencies it creates offsite is offsite they've got all these linear saws and optimized saws which create cost benefits. So if you're on site and trying to decide which bit of timber to cut in which place so that you optimize your wastage, whereas these offsite fabricators have all of those innovative technologies and systems that can actually optimize the way that it cuts product, so it becomes the most beneficial way and cost efficient way to assemble these things. So that's really one of the key benefits is utilizing those innovations and technologies to maximize or minimize cost in terms of the actual materials. And then you also get the added benefit that when it turns up on site, you get those installation benefits as well. So yeah, there's a sort of a double whammy there. In terms of design, it's if you're doing your job properly, it's probably not going to be too different between the two, as long as you're taking all of those into consideration. But they're the main benefits that these guys can look at.
And certainly with cassette floors, there's obviously that sort of safety element as well. It's a much safer way to install them rather than to be building that on site and potentially having a sort of risk of a fall from height. Look at definite benefits.
The other thing too, Alistair, is the stabilize, like you said, that part of it and stabilizing it. So when it goes out, having the sheet floor already fixed in place when they land these things on site, you don't have to go and temporarily brace the trusses before you put the flooring on. So it's instantly stable as soon as it turns up.
A question here about sort of mixing different screws. Quite a few timber suppliers will provide other screws and fixing mechanisms, mixing Pryda, MyTech and other type systems. What are your thoughts there?
Yeah, look, you have to be careful with substitution because you can get yourself in a bit of hot water. We looked at that graph before, which had different values for different screw fixing. So you just need to make sure that if you are substituting, that you're substituting with, knowledgeably substituting, not randomly substituting. So you need to be a bit careful in that space. Usually with, when a specification comes out of a piece of software, certifiers are normally checking to that specification that comes out of the software. So just be, really careful with substituting products, because it could come back to bite you.
Somebody's actually asked a question here, will there be a webinar on cassette systems? And even though it's not scheduled into the program, I think this year we'll definitely be looking at doing one of those in the future. So there's some joint work happening between Pryda, MyTech Multinail and Myer Timber at the moment, just upgrading the business plan, particularly for ground floor cassette systems. Because we certainly believe that a raised timber floor on a constrained site, like a sloping site or a flood inundation zone or a reactive clay, is a much more efficient way than a concrete slab on the ground, which is simply the way builders want to do it. We've done this 5 years ago to demonstrate that over about a 400 or 500 millimetre fall, a raised floor is a more cost-effective offer. But the builder these days wants someone to supply a working surface on a site on a specific date for a specific cost, and that's where the cassette systems work well for the frame and truss sector. So we're doing that update to that at the moment, and when we have those results, we'll definitely be doing a webinar, probably early next year, on cassette systems, both upper floor and ground floor, which I think's much more interesting for the residential market at the moment. Still got some questions coming in, which is good. What are the maximum cantilever capabilities for floor trusses for backspan scenarios and also parallel span scenarios?
With backspan, we typically go at least 2.5 times of the cantilever span. So I've seen, floor trusses going out 1800 as a cantilever, but obviously that's subject to the depth. So if you're trying to go out 1800 with, 240, 250 floor space, that's a bit of a challenge. But if you can get up to that sort of 400, 450 depth, then those are the sorts of cantilevers that you can run with a floor. You just have to be a little bit careful with the dynamic effects on the cantilever end, because the way that dynamic performance is usually measured is through the central span of the truss, and it's a deflection calculation that tries to maximise the stiffness for the floor truss. So you just have to be a little bit careful when you go further out with those cantilevers that you're tying it at the end with a rim beam, so that when you get on the end of those trusses, they're joined together with a continuous beam member that helps to redistribute that point load at the end of the cantilever. That's really one of the key things. But yeah, look around about 1800, 15 or 1800 is about the spot that I'd say, okay, that'll just about do it.
So a question here actually about the floor systems, and can they support thin up to 60 mil poured concrete floor slabs? I assume this is probably for acoustics more in the mid-rise section than residential, but yeah, you might comment on that.
Yeah, look, they can. Again, it gets back to, because it's a uniformly distributed load, the key things are really, just making sure they're designed for those loads. So typically over the span of a truss, they will take, 3, 4, 5 kPa of live load. And so having, 40, 50 mil of screed isn't really going to bother it too much, as long as you might have to shorten the spans a little bit. But those are certainly doable.
I've had a couple of questions actually just on girder trusses, which is always of interest, particularly for, the designers. How can they guess or, where a girder truss location might be? Are there any sort of rules around that people should know?
Yeah, look, 2400 is about the industry standard for girder trusses off the end walls. So if you run that as a ballpark figure, sometimes they'll move girders to avoid conflicts with lintels. So they might try and shift a girder back by a little distance to try and avoid it landing in the middle of a lintel. But 2400 is normally a good rule of thumb mark for most girder stations for hip ends.
Okay, maybe just one last question, because we're just about up to time. How much impact does photovoltaic cause on truss design due to wind forces? Yeah,
look, those, I think we touched on that before. The flat to the roof is minimal impact, because the solar panels are quite light. They're only sort of 15 to 20 kilos a square metre. It's really when they get on the raised platforms that it becomes a bit of a problem, because you end up having almost two separate roof planes, both attracting wind loads. and those loads need to be resisted by the trusses. And they normally only use those raised platforms on shallow pitch trusses, and because they're not mechanically as beneficial as a deeper or a higher roof pitch truss, because you've got that greater depth on the higher roof pitch truss, that's when you just need to be a little bit more careful when you have solar panels on raised platforms. They attract almost double the wind loads on the roof, on the solar panel itself and on the roof, and you need to make sure that the actual structural anchoring at the ends of those platforms is those loads are passed to the truss underneath and they're designed appropriately.
Mm. Oh, well, that's fantastic. I want to thank you again, Ian, today. That's been a terrific presentation, some really practical things passed over, but it's been great to have a sort of bit more of an extended Q&A session at the end, because it's good for people to be able to ask the specific questions. You know, you often don't know what people have an interest in, so it's been great and some terrific questions that have come in from everyone. So thank you for those as well. So thanks once again, Ian. On behalf of everyone here, if we could clap, we certainly would, but no, it's been terrific. Everyone, just remind you about next week's Wood Solutions presentation. So 25th of August, it's entitled Elements of Enriched Environments. And we're very fortunate to have Ty Farrow, senior partner with Farrow Partners Architects from Toronto in Canada, will present there. They do some amazing work, as you can see here with the Credit Valley Hospital picture that we've got here, particularly around that sort of biophilic use of timber, and just as the title says, really enriching the environments that people live and work in. So thanks once again for joining us today. It's been another great webinar, and we look forward to catching up with you again at the next webinars. Bye, everyone.